Okay, so thank you for coming. My name is Georgios. I will talk about Plasma, which is a scalability solution. And my current affiliation is with Loom Network, a company which builds games which are built on scalable infrastructure. So what is the problem? We have some issues on Bitcoin. With the current state, it's 1 megabyte blocks. Even with Segwit, we cannot get above like 7, maybe 10 transactions per second. For Ethereum, when you do 21,000 gas transactions, which are simple value transfers, you can maybe get like 28 transactions per second. But if you want to do more complex transitions, which is what's interesting, the throughput drops. And I should say that these two slides are taken from Paddy McCrory from King's College. So we have this problem where we either want it to be decentralized, and we also want it to be verifiable by the public. And the problem exists that if you have too many users, you cannot have a large set of validators. So what can you do about this? First way is that you can go with a centralized approach, which we really do not want. The other approach is to go for alternative infrastructures, which so far I don't think any has proven of its value. Other approaches, such as the one that Ethereum 2.0 and other chains are taking, is to shard. So you have a main chain, you have multiple chains, and each shard essentially has your throughput increases linearly with the amount of shards. And then we have the off-chain approach, where you take the state out and you try to design it so that even if something goes wrong off-chain, you can always go back to the original main chain to go to court and solve the dispute. And I will talk about Plasma, which is essentially a framework for creating what we call non-custodial sidechains. But let's talk about firstly what is a sidechain and what's the interest in it. So imagine that you have two chains, the parent chain and the Plasma chain, or the sidechain. What happens is that you lock your funds in an escrow contract. It can be a multisig if you do it on Bitcoin, or it's some smart contract on Ethereum. And what happens is that the Plasma chain, which is aware of what's happening on the main chain, it creates some assets. When it creates these assets, you are basically able to transact with it. And the whole idea is that any transfers that you make on the Plasma chain or the sidechain, they're very, very fast because you essentially have like a less decentralized setup. And when you want to withdraw your assets, you do what we call an exit, or you can burn the asset. And basically what happens is that after a few blocks, the asset that you had locked originally, it gets unlocked. So in sidechain terms, this is called the two-way peg. And the logic is that you lock in the main chain, you mint on the sidechain, you burn on the sidechain, and you unlock on the parent chain. And basically, there's one problem with this, that if you want to do scalability, I will claim that there is this trade-off between scalability and security, which might not have an impossibility result, but it may as well be. So what we want to do is that when you start centralizing the chain to make it more scalable, you have the danger that if the sidechain manager, essentially the validator set of the sidechain, does not want you to make the exit, the withdrawal, because they're censoring you, you're not able to do it. You're not able to get your funds out. So alternatively, what we do in Plasma is that we say, OK, we will commit the state of the sidechain to the parent chain all the time. So what happens is that essentially each Plasma block gets committed to the parent chain, and then you buy some database manager, which we call the operator, usually for convenience. And basically what you have is essentially a sidechain, which is controlled by one party, which commits all its state, all Merkle roots of its state updates to the parent chain. And what we do is that we design a thing called an exit game. So when you want to withdraw, instead of allowing instant withdrawals, what we do is that we introduce some delay. And the delay is done so that if you, for some reason, try to make an invalid withdrawal attempt, some other party will come and show up, and they will say, no, your attestation is invalid, and they will challenge, and your challenge exit will get cancelled. But if there is no challenge on the exit, after you wait some challenge period T, which is a security parameter of the system, you can finalize your exit, and you can take your funds out of the Plasma chain. The notion here of somebody challenging, it introduces a liveness assumption. So there must be people watching. So this is like a thing to take into account. And this is common in all layer 2 solutions, so even in Lightning Network, in any kind of state channel network or Plasma, you always need to have some parties which watch within this challenge period. Because if nobody challenges during this period, yes, fraud can happen. Specifically, my focus is on a variant of Plasma, and there have been many, many variants of Plasma, called Plasma Cash. And the whole notion of it is that just like cash, when you deposit, let's say, 5 Ether on the smart contract, on the sidechain you get a 5 Ether bill. And much like cash, it has a serial number, and you cannot split it. So this means that if I have a 5 Ether bill and I want to give it to Ben, I need to give him the whole bill. I cannot split it in any way, because if I split it, like in real world, like you cannot split a coin. And so this introduces an issue with fungibility. But we assume that we use non-fungible transactions. And when you want to transact, when you want to send your coin to someone else, you need to refer to the block that you received it and the parent block. And I will explain why you need that. And when you want to withdraw your funds, you also need to reveal 2 transactions. The transaction in which you got the coin and the parent transaction. And this is part of the exit game. So what can happen? And before I can get to that, let me just say that the Merkle tree structure we use a sparse Merkle tree, and thanks to Kelvin for making this graph. Basically, the sparse Merkle tree is an ordered Merkle tree where each leaf, so if I have the coin with ID 10, it's the 10th leaf in the Merkle tree. And this, it allows us to do inclusion proofs, just like all Merkle trees. You just provide like log n hashes which show that your element was part of the Merkle tree. But it also has this nice property that you can do exclusion proofs, which by exclusion proofs, you basically say that nothing was included there. So an exclusion proof of coin 10 is that showing that at the index 10, there was nothing there, while an inclusion proof is showing that there was some transaction there. So now we'll talk about how transfers, exits, and challenges work. So let's take a simple example. So we have like Alice, the usual suspect. She deposits 5 Ether on the Plasma contract, and she gets like a 5 Ether NFT, as we say, like on the Plasma chain, from nowhere. And now she has it in block 1, let's say. So at block 2, she makes a transfer to Bob, let's say. And when Bob gets the coin, he must verify, since the coin's deposit, that the coin has valid history. What does this mean? That it has valid inclusion proofs, there have been no double spends in its history, and so on. And yes, the Plasma chain has a UTXO model. It's not like Ethereum where you have accounts. You have coins, each one with its own UTXO history, and you need to verify that. So let's say that block 3 comes, like the coin is not moved, so we don't care. By block 4, like when Bob sends the coin to Charlie, not only does Charlie have to check the coin that it was spent in block 1 and 2, he must also verify that it was not spent in block 3. Because clearly, if there was a spend in block 3, the coin was double spent, and we do not want that. And this introduces a main thing about the receiver of a coin, that they need to verify the coin's history. And this can have like non-insignificant bandwidth requirements, because you need to download the proofs from somewhere. And when I say verify coin history, it means that you download all the Merkle proofs that prove inclusion and exclusion in your coin. And then if he wants to exit, he just like verify, he just points at the when he received it and the parent. And now I will do like some like very basic graph like about how like the lifeline of a coin is. So when you deposit it, the coin is like at the state QA. When you want to make an exit, and if everything goes well, like you exit your coin, it goes into the next state. 7 days pass, let that be the challenge period, then you can finalize the exit, and then you can withdraw the coin. So that's a happy case. But then, if you have a non-interactive challenge, and I will talk about how each challenge works later, if I make an exit and within that time frame somebody challenges, my exit gets cancelled. It's gone, it's again to the initial stage. In the interactive challenge case, what happens is that you have like a counter, which essentially counts how many interactive challenges the coin has. And in order to finalize an exit for a coin, it must have 0 interactive challenges. So if 7 days pass and nobody responds, somebody can call, again, finalize the exit or finalize the challenge, and the coin is no longer being exited. If somebody responds to all challenges, very explicitly all challenges, then you're back in the happy case. So let's talk about how each challenge works. So we have Alice, again, who has some coin that she received in the past. She has verified the history. she spends it, and then immediately after spending it, she goes to the parent chain and she calls exit. And when she starts the exit, the Plasma contract, it's not aware of the sidechain full state. It cannot know that the coin was spent. What it knows is that there was some commitment later. So what Bob simply does is that he goes to chain and he shows, no, this coin was spent, and the exit is cancelled. So that's the first one. It's pretty straightforward. The other approach is that Alice sends the coin to Bob, and Alice, in a later block, she double spends, so she has a coin that she has already spent, and she sends it again to Charlie. And if Charlie wants to exit, he basically is trying to exit double spend, and in order to cancel an exit of a double spend, you reveal an earlier spend from the exit. And the earlier spend, it must be between the exit and the exiting block and the parent blocks. So in this case, this is the exiting block, and this is the parent block. And you challenge by showing a challenge between. And in the implementations, we call this challenge after, challenge between, and challenge before. Because what can happen is that we cannot have trust assumptions about this database manager, the operator. And what may very well happen is that the operator makes an invalid state transition. By invalid state transition, I mean that Alice is normally the last valid owner of the coin, but for some reason the operator gives the coin to Bob in their own database. What happens that then Bob transacts with it, and let's assume that Bob, Charlie, and Dylan, they're all friends, and they want to take Alice's coin. And if they were honest parties, they would verify the coin history, they would see that there is no spend from Alice to Bob, and they would reject the coin. So when Dylan exits, Alice can she can basically claim that she's the latest owner of the coin, and if there is no response to that, so this is the interactive challenge, she basically cancels the exit. But if, in fact, like there was a spend from Alice to Bob, then Bob, or basically anyone else, they can respond to the challenge of invalid history. And this will decrement the counter for the challenges, and then the exit can go through. So these are the three types of challenges. So why is this secure? Is this secure? And let's see. And will people do it? So firstly, the assumption, as I said, is that somebody is able to make a challenge. So when somebody starts an exit at, I don't know, T0, there is like time T until the exit can be finalized. So this means that somebody must be able to get their exit transaction included in a block. So let's say that some time passes and at T1 somebody broadcasts a challenge. It is the case that a miner could censor the challenge transaction. And for example, if T1 was later, so if a miner is able to censor the transaction for long enough, then the attack will succeed because the challenge doesn't get included in time. So somebody must watch, and they must be able to include their challenge transaction in time. And basically, there is some safety condition that we want to uphold for this. And we have done a lot of work on making sure that an attacker will never do this. So what happens is that when you exit, not only do you pay the gas costs, you also put up a security bond. So you say, I put up 1 Ether, and I say that if somebody is able to challenge my exit, I forfeit that Ether. It's like you put skin in the game in this thing. So if there's no challenge, the attack is successful, and the attacker gets back his bond, and he just has to pay the gas costs. But if the attack fails, and somebody challenges, the attacker, we assume that this is a powerful adversary, they can also go for a front run. What is a front run? It's essentially, I make a transaction, so attacker exits, someone challenges, and then what the attacker wants to do is that they want to front run the challenge. They're gonna challenge themselves. Why do they want to do that? Because the bond that they pay initially, it goes to the challenger. So if they are able to challenge themselves, they'll get the bond back, and the cost to attack is significantly reduced. So what we do to save that is that we only refund the part of the bond, and you can, I don't know, you can send the rest of the bond to charity. So you can say 0.6 ETH out of 1 will go to charity, or just burn it, send it to 0x0. And yeah, I will skip this. We have some the expected reward of the attacker in this scenario, it must always be less than 0. So basically what you do is that you parameterize the challenge period and the bond so that an attacker will never basically decide to attack because the expected reward is less than 0. And so far so good, but what can we do to get better? So as I said, the Plasma cache, it has non-fungible coins. So this means that you cannot make arbitrary denomination payments. So I have to either, if I want to make a 7 Ether payment, I have a 10 Ether coin, or in my example, you need to get some change in return. And in order to get this change in return, you need to have like some notion of atomic transaction, so that the operator includes a transaction that sends you 7 ETH, but it also includes another transaction which you receive, that you send 7 ETH and you receive 2 ETH. So you need a construction that is able to do that. Another approach for arbitrary denomination payments is that you essentially create each coin, essentially it becomes a payment channel between the user and the operator. And if you have like a 5 Ether coin and another user has a 3 Ether coin, you have capacities instead of values. So the 5 Ether coin, it can have any value from 0 to 5, and the other one the same. So what you can do is that you reduce your coin by some amount, so a 5 Ether coin becomes 3 out of 5, and you have another coin, which is, let's say, 1 out of 3, and you increase it to 3 out of 3. So you need to do this atomic transaction, which reduces one and increases the other one. And the other approach to arbitrary denomination payment is that instead of having a 5 Ether coin, you get 100 coins, each one being 0.05 ETH. And essentially, instead of having bills, you have change. And there is a team that's working on this, Plasma Group, and they will be around. So if you want, like, you can maybe hack or work with them, right? And they have an implementation of this. But the thing is that this has like more complexity than the previous constructions. Another problem is that we want to reduce data requirements even more. Because when I receive a coin, I need to validate the coin's history, which means that if 1 year has passed and nobody has transacted with the coin, I basically need to download 1 year's worth of exclusion proofs, which if you like commit often to the chain, this can be maybe like 1 or 2 gigabytes, which it may sound or may not sound big. But for light clients, which are on your mobile, you cannot assume that you will have like 2 gigabytes for each coin. And the solutions to this are either you checkpoint, so essentially you say that every 10,000 blocks, this is the latest valid state and nobody can challenge with an earlier one, and so you only need to verify the state up to the latest checkpoint. The other thing that you can do is that basically instead of committing per 15 seconds, you can commit per minute, which reduces the amount of data by 4, or any amount you want, but this has an impact on finality because your transaction doesn't get confirmed fast enough. Other approaches which are more like with moon math, as they call it, like it's either with some snark or stark construction, which, if I'm not mistaken, there was an implementation at ETH Singapore that did plasma cache history compaction with zero-knowledge snarks, or with RSA accumulators, which was a very widely discussed mathematical topic like in the last few months for the plasma community. Finally, this is a UTXO chain that can only do payments. So what if we could do like smart contracts on Plasma? So there are some approaches to this. Some users are doing EVM inside the EVM during the verification, but it's not exactly clear how this works. So this, I believe the project doing that here is LibDAO, so you may also want to talk to them about this. But the approach that I prefer for this, it's like if we could do state channels on Plasma. So essentially you would fund the channel with a Plasma coin and you would settle the transaction to Plasma. And this has the benefit that you can do smart contracts on the Plasma chain, which is nice. You can do, for the payment channel, you have this very nice property that the funding transaction of the channel and the settlement, it still costs no fees. So you're essentially not at layer 3, but you have like 2 layer 2 solutions interacting with each other. And in order to do this, you basically need to have a multi-sig account on the Plasma chain and some time locks, so either with a hash time lock contract or something similar. And this is ongoing work. So let me just summarize what I just said. So Plasma is a non-custodial sidechain where you commit the blocks to the parent chain. And some people have started calling this commit chains, which is a nice term to avoid the confusion. It allows you to do gasless payments without any onboarding costs, which is a huge advantage over channels, because in channels you need to create a transaction on chain to participate. A very, very nice way to think about it is simply a compression mechanism. Instead of putting all data on chain, you just put 32 bytes per block. It has the liveness requirement that the users, every challenge period, you need one honest party. That's it. Like if you have one honest party, you can do that. and many things have been built on with one honest party assumption, say, for example, the sapling update for Zcash. So we can say that this is like an okay assumption for liveness. And the current work in progress is to do smart contracts via channels, arbitrary denomination payments with the ways that I proposed, or even lighter light clients. And thank you for your attention. And I've written a technical document that explains how this thing works. And I also have all the code open sourced, so you can look at it. And thank you very much for your attention. And happy to take any questions on the topic.
Hello. Yes, thank you for talking today. I appreciate it. I'm just kind of wondering about your perspective on the distribution of like layer 2 solutions and how you think this will all pan out. Do you see, because like channels like this and Plasma are very capital like intensive, like you are committing to locking up resources into this. So I'm just kind of wondering, like, do you think like there'll be some like database where like things are like minted on chain and you'll just use a database and it's held centrally somewhere like an exchange? Do you see like people using Plasma? Do you see like a mix, or how do you see it like all?
Is the question about interoperability of chain protocols?
Yeah, and just like the distribution, do you think it's going to be like primarily one or like a mix of all of them?
So I'm not sure I get the question. Like, it is possible to have like, can you like maybe rephrase the question because it's not clear to me?
No worries. TLDR, how do you see layer 2 panning out and what role does Plasma play?
Okay, Plasma is not like, it's not like, I don't think there's one winner. Like, so there is like one thing that I've been talking about lately, that in Bitcoin, you have Lightning Network, it's one network that can accrue all the value, and you have like people building on Lightning. On Ethereum, like, and all other like chains, you have like multiple layer 2 protocols, and it's starting to get hard to figure out which one will accrue all the network effects for that. So interoperability is a good thing to have, but eventually I think we'll get to a stage where you will have like either one large Plasma chain, or you will have a generalized state channels framework like counterfactual, for example, which is I'm not sure if I answered the question though. Yeah. Okay, thank you very much. And we'll have Ben from Neon District now.